Hello everyone. In today's session, we are delving into a classic problem in computer science and mathematics, which is Tower of Hanoi. Before we get started, let's quickly overview the agenda for today. First, we will start by understanding the goal of Tower of Hanoi problem, and then we will explore the rules and constraints involved in Tower of Hanoi problem. Moving further, we will walk through the problem visually, showcasing the initial, intermediate, and final states. And this will help us to visualize the movement of disk between the rods. After which, we will dive into the recursive algorithm behind the Tower of Hanoi problem. Next up, we will go through the pseudocode line by line and a flowchart providing a visual demonstration of how the algorithm operates. Finally, we will wrap it up by Python code to solve the Tower of Hanoi problem. And we will run it to see the solution in action. Before we get started, let's see what is Tower of Hanoi problem. The Tower of Hanoi is also known as Tower of Brahma or Lucas Tower. It is a mathematical game or puzzle that consists of 3 rods with n number of disks of different diameters. To be simple, it is a pyramid puzzle, which is a mathematical game using 3 rods and various number of color disks stacked in descending order with a larger disk on the bottom and the smaller disk stacked on top. And this creates the iconic cylinder or pyramid shape that the Tower of Hanoi is known for. The Tower of Hanoi can be played with any number of disks. However, most toy versions comes with anywhere from 5 to 9 disks. The Tower of Hanoi was first introduced by the French mathematician Edward Lucas in 1883, and many myths about its origin have been shared. The most popular one is the famous Kashi Vishwanath temple in Varanasi in the Indian state of Uttar Pradesh is regarded as one of the holiest places in Hinduism. Lord Brahma, the Hindu deity of creation, connects this temple with the version of puzzle presented here. This temple containing a room with 3 massive pillars wrapped with 64 golden discs. But this story was spread tongue-in-cheek by a friend of Edward Lucas. If the element of history were true, and if the priest were able to move the disk at the rate of 1 per second, using the smallest number of moves, it would take them 2 to the power of 64 minus 1 seconds, or roughly 585 billion years to finish, which is about 42 times the estimated current age of the universe. In some versions, other elements are introduced, such as the fact that the tower was created at the beginning of the world, or the priest or monks may make only 1 move per day. Acting under the rule, if the priest continually moving the disk one at a time, it is believed that once the Tower of Brahma is complete, the world would end. It eventually became included in the Cambridge Neuropsychological Test Automated Battery, developed in the 1980s to measure memory, attention, reaction time, decision making, and response control. The Tower of Hanoi has also had a prominent role in pop culture and video games. Most notably in 1966 episode of Doctor Who, where Doctor was forced to play a mind-numbing 1023 move Tower of Hanoi puzzle called Trilogic Game. In 2011, the blockbuster movie Rise of the Planet of the Apes, the Tower of Hanoi problem was featured as an intelligent test for the apes. This puzzle requires a considerable skill and mental aptitude, also tests one's cognitive functioning as well as programming skills. It is also an unspoken testament that everything we know might only exist because of the supremely powerful and super intelligent God. Now let's see how to solve the Tower of Hanoi. The objective of the puzzle is to move the entire stack to the another rod. The minimum number of moves required to solve a Tower of Hanoi puzzle is 2 to the power of n minus 1, where n is the number of disks. For example, in a 3-disk problem, you will have to use a minimum of 7 moves. So every time you add another starting disk, that minimum number of moves is doubled plus 1. So for 4-disk problem, it takes 15 moves, and 5-disk problem takes 31 moves, and so on. However, it seems simple at first. There are few rules that makes this classical puzzle game favorite among the puzzlers. And these are the 3 fundamental rules for the Tower of Hanoi problem. Rule number 1. Move only 1 disk at a time. That is, you are limited to picking up and moving just a single disk at any given moment. Rule number 2. You can only move the disk that is on top of a stack. Rule number 3. You can't put a larger disk on top of a smaller one. Now let's talk about the visual representation of the Tower of Hanoi. Imagine you have 3 pegs labeled 1, 2 and 3. On peg 1, you have a stack of disks with different sizes, with the smallest at the top and the largest at the bottom. Now the smallest green disk, which is the uppermost disk on the stack, is moved from rod 1 to rod 3. Next, the uppermost disk on rod 1 is blue colored disk, which is shifted to rod 2. Now the smallest disk on the rod 3 is shifted back onto the top of the rod 2. So now the largest red disk is allowed to be shifted from rod 1 to its destination rod 3. Now the 2 disk on the rod 2 has to be shifted to its destination rod 3 on the top of the red disk. So the smallest green disk on the top of the blue disk is shifted to the rod 1. Next, the blue disk is permitted to be shifted to its destination rod 3, and that will be stacked on the top of the red disk. Finally, the smallest green color disk is also shifted to the rod 3. And now the Tower of Hanoi for 3 disks has been solved. Now let's understand the recursive algorithm for Tower of Hanoi. In recursive algorithms, the base case and the recursive case play critical roles in defining the logic and termination conditions for the recursion. The base case defines the simplest scenario where the algorithm can directly provide a solution without further recursion. The recursive case defines how the problem is broken down into smaller, that is, the more manageable subproblems. Both are necessary because without base case, the recursion would continue indefinitely, that is, leading to never-ending process. The recursive case allows the algorithm to divide the complex problem into simpler instances, making it more manageable. To ensure the completeness, termination, and efficiency of recursive algorithm, they provide a clear structure for solving problems in recursive manner. Now let's break down the algorithm line by line. In line 1, we define a function called Tower of Hanoi that takes 4 parameters: n, the number of disks; source, the source peg; auxiliary, the auxiliary peg; and target, the target peg. And next we have the base case, and this line checks if there is only one disk to move. If it is true, the algorithm executes the following line. So in the base case, when there is only one disk, it prints or represents the move of the smallest disk from the source peg to target peg. If the condition in the base case is false, that is, if there exists more than one disk, the algorithm proceeds to the recursive case. The line 5 is the first recursive call. It moves the top n-1 disk from the source peg to the auxiliary peg, using the target peg as a temporary peg. After the first recursive call, the line 6 represents the move of the nth disk, that is the largest disk, from the source peg to target peg. Line 7 is the second recursive call. It moves the n-1 disk from the auxiliary peg, where they were temporarily moved in the first recursive call, to the target peg, using the source peg as a temporary peg. So this algorithm recursively breaks down the puzzle into smaller subproblems until it reaches the base case. That is when there is only one disk to move. Now let's refer the pseudocode for Tower of Hanoi algorithm. The pseudocode we are looking at is a direct translation of the algorithm. The pseudocode and the algorithm are equivalent for the Tower of Hanoi. So this pseudocode follows the same recursive principle as the Tower of Hanoi algorithm and demonstrates the movement of disk between the pegs in similar manner. In line 1, we have a function named tower, and this function is designed to be called with specific parameters: n, the number of disk; source, the source peg; auxiliary, the auxiliary peg; and target, the target peg. The line 2 is the base case. When there is only one disk, it directly moves the disk from source peg to target peg. In base case, the line 3 represents the actual movement of the smallest disk. The else part is for the cases where there is more than one disk. Line 5 is the recursive call, which will move the n-1 disk from the source peg to auxiliary peg. This step is similar to step 1 in Tower of Hanoi algorithm. Line 6 represents moving the largest disk from the source peg to the target peg. And this step is equivalent to step 2 in the Tower of Hanoi algorithm. Line 7 is another recursive call, which will move n-1 disk from the auxiliary peg to the target peg. This step corresponds to step 3 in the Tower of Hanoi algorithm. Now let's understand the flowchart for Tower of Hanoi problem. The flowchart starts with start symbol, and then we have a function definition block in which we define a function and its parameters. At start, we check if the number of disks denoted as n is equal to 1. This is our first decision point. If n is equal to 1, it means if we have a single disk, then we will move the disk directly from the source peg to target peg. Now we mark n for the base case when n is equal to 1. If n is greater than 1, we enter the recursive steps. In first recursive call, we call the Tower of Hanoi function recursively to move n-1 disk from source peg to auxiliary peg. Next, we have an action block to move disk n, which represents moving the largest disk from the source peg to target peg. Now we have a second recursive call, which calls the Tower of Hanoi function recursively to move n-1 disk from the auxiliary peg to target peg. And we finally end the flowchart for the case when n is greater than 1 after performing the recursive steps to the end of the entire flowchart. And so far we have seen the flowchart that helps to visualize the sequence of action taken in Tower of Hanoi algorithm. And here is the Python implementation for Tower of Hanoi algorithm. In line 1, we declare a function named Tower of Hanoi, which take 4 parameters: n, source, auxiliary, and target. Line 2 is base case check. It checks if there is only one disk, that is n equals 1. If it is true, it executes the block of code within this if statement. And the else part is recursive case. So if there is more than one disk, it executes a block of code within the else part. Line 5 is the first recursive call. So this line calls the Tower of Hanoi function recursively with n-1 disks, which moves them from source peg to auxiliary peg. And this line of code is print movement. So this line prints the movement action for the largest disk n, that is from source peg to target peg. And the line 7 is the second recursive call. Here we call the Tower of Hanoi function recursively with n-1 disk, moving them from auxiliary peg to target peg. Here n equals 3 specifies the number of disks that we want to solve. That is, we are setting a variable n to 3. So in line 10, 11 and 12, we define 3 variables, that is source peg, auxiliary peg, and target peg, representing the names of the 3 pegs A, B, and C. In line 13, we have a print statement. It prints a message indicating that you are solving a Tower of Hanoi problem with a specified number of disks. The F before the string indicates that this is an F string. Inside the string, n within the curly brace is a placeholder for the value of the variable n. When the string is printed, Python evaluates the expression inside the curly braces with the actual value of n at the runtime. When n equals 3, the printed string becomes solving Tower of Hanoi with 3 disks. And finally, we have a function call. So this function calls the Tower of Hanoi function with the specified parameters. This initiates the Tower of Hanoi algorithm for the given number of disks and peg names. The output will show the sequence of moves required to solve the Tower of Hanoi problem with 3 disks using the pegs A, B, and C. And the function Tower of Hanoi is responsible for printing each step of the solution. Now let's execute this program. This code runs the Tower of Hanoi algorithm for 3 disks and displays each step of moving the disk among the pegs. You can also modify the n variable to solve the problem with different number of disks.